Now audio video are clear. Let me check once. Now audio video are clear. Yes, okay, thank you. Okay, thank you all. Welcome to Gate Academy. How are you all? Yes, very good morning everyone. Okay, let's get started. So in previous class we had discussed about what is mean by transformer and what are the features of the transformer, and after that we had discussed about nameplate details and applications of the transformers. Okay, the transformer is a static device which transfers electrical power from one circuit to another circuit at same frequency. And what are the features of the transformer? Transformer is a constant power device, constant frequency device, constant flux device, and also transformer is treated as 180-degree phase shifting device. That means the EMF induces in the transformer opposes applied voltage by 180 degree. That means the phase difference between the applied voltage and induced EMF is equal to 180 degrees. Okay, this part we had discussed in the previous session, and after that we had discussed what are the applications of the transformer. So majorly transformers are used in the transmission system and distribution system. The transformer which is used in the transmission system is known as power transformer. The transformer which is used in the distribution system is known as distribution transformer. And what are the difference between the power transformer and distribution transformer? We will discuss in the next coming sessions. Okay, and after that transformer is used as a coupling device, and it is also used as isolation of the two circuit. Okay, these are the application. And rating already we have discussed: power rating, voltage rating, frequency rating, and these are parts we had discussed in the previous session. Okay, so today we will discuss about another topic of the transformer. So that is the operating principle and working of the transformer. So operating principle, what is the operating principle of the transformer, and after that what is the meaning of working of the transformer. So working of transformer in the sense, that is, how does EMF induces in the transformer windings. All of you clear my point? Working in the sense, how does EMF induces in the primary winding as well as the secondary winding of transformers. So initially, what are the objectives of these topics? Objectives means the what topics to be discussed in this case. So what are the question to be discussed in this topic? So first one we have a question. So that is a how to find out, okay, how to find the magnitude of the flux. Okay, this magnitude of the flux in the winding. Okay, this is the first question. And next one is a how to find the direction of the flux. This is also another objective of this topic. And next one, third one, so that is a how to find out, okay, the magnitude of, okay, this magnitude of induced EMF. Okay, this is another possibility of the question. And next one, how do we find, okay, direction of the induced EMF. Okay, so this is a direction of the induced EMF in the transformer winding. So these are all objectives. Okay, there is a possibility of the question. So one is how to find out magnitude of the flux, and how do we find direction of the flux or direction of the magnetic field. And second one, third one is a the how do we find out magnitude of induced EMF in the primary winding as well as secondary winding of transformer. And fourth objective is how do we find out direction of the induced EMF in primary winding and secondary winding of transformer. So these are the objective of this topic. So let's get discuss one by one. Okay. So first we will discuss about, so that is a operating principle of, okay, this is the operating the principle of transformers. So what is the operating principle of the transformer? So we know that the transformer operates on the principle of Faraday's laws of electromagnetic induction. So this is the operating principle is a, the transformer operates on the principle of the Faraday's laws of electromagnetic, okay, electromagnetic induction. So we have a two laws, one is the Faraday's laws of electromagnetic induction first law and Faraday's laws of electromagnetic induction second law. So according to the second law, so what is the, so this second law here, so this is the second law. So what is the statement of this law? The statement means whenever the air, a coil is excited with the AC supply and EMF induces in a coil or winding is a directly proportional to the rate of change of flux linkage. So what is the statement of this one? So an EMF induce, the EMF induce in a coil, okay, or winding is a directly proportional to, okay, this is a directly proportional to the rate of change of flux linkage, change of the flux, the linkage. I will tell you what is the meaning of flux linkage. So mathematically, how do we write this one? So EMF induced in a coil, okay, this EMF induced in a coil or winding, so is a directly proportional to the rate of change of the flux linkages here. So this is a mathematically, so with the statement of Faraday's laws of electromagnetic induction. So where the flux linkage, so what is the meaning of that? This we can say that, this we can say that is the psi is equal to the rate, that is the number of turns of the winding or coil multiplied by flux. That means how many number of turns, how much amount of the flux links with the number of turns is known as a flux linkage. All of you clear point? So this is a operating principle of transformers. Okay, I repeat once again, listen. Transformer operates on the principle of which law here? Faraday's laws of electromagnetic induction. So what is the statement of Faraday's laws of electromagnetic induction? So an EMF induces in a coil is a directly proportional to rate of change of flux linkage. So what is the meaning of flux linkage? The flux linkage means how much amount of the flux links with the number of the turns. Suppose we have a coil, okay, like this. So now there is a flux. How many number of the turns? For example, n number of the turns. Suppose we have a flux, okay, phi amount of the flux, okay, here. So how much amount of the flux linking in this coil? So that is known as a flux linkage. So we will discuss in detail, okay. The first, what is the statement here? An EMF induced in a coil is a directly proportional to the rate of change of flux linkage. So mathematically we can write the E is a directly proportional to rate of change of flux linkage. Okay, is that clear everyone? So what are the first one? Operating principle. So next we will discuss how does EMF the induces in the coil, or how does EMF induces in the primary winding as well as the secondary winding of transformers. Okay. Is that clear everyone? Do you have any question? Good morning all, very good morning. If you have any question you can ask. Okay, I am here to discuss. Don't think about is it easy or difficult. I am always welcome any type of the question from you. Okay, very good. So next one, so that is a working of transformer. I already mentioned that. What is the meaning of working? Working in the sense, how does EMF induces in the transformer windings? So this is the meaning of working here. How does the EMF induce? Okay, how does EMF induced in the coil or windings of transformer? So that is the meaning of working of transformers. So what are the basic requirements? Sometimes we have a question. So what are the basic requirement to induce the EMF in a transformer's winding? Or what are the basic requirement? Are you getting my point? So what are the basic requirement to induce the EMF in a coil, or what are the basic requirement to induce the EMF in a winding? So first one is a basic requirements. Okay, the requirement to induce EMF in a coil or in transformer windings here. So what are the basic requirement to induce the EMF in a coil or transformer winding? The first requirement, okay, first one is the set of conductors. Okay, or so what is the meaning of set of conductors here? So that is nothing but group of the conductors. Okay, and second one is the stationary magnetic field. Okay, this is the stationary magnetic field. So what is the meaning of the stationary magnetic field? So we know that magnetic field means the region around the magnet is known as a magnetic field. So what is the stationary magnetic field? So that means conductor is also stationary, but that means winding is also stationary in the transformer, and magnetic field produced due to this, okay, due to the magnetizing current also stationary. That means speed of this magnetic field is equal to the 0. So that is a stationary magnetic field. And third requirement is the relative time variation. Okay, this is a relative, the time variation between the magnetic field. So between the magnetic field and the set of conductors. Okay, all of you clear point? So these are the three requirements to induce the EMF in a transformers. So one is the set of conductors, okay, the stationary magnetic field, and relative time variation between the magnetic field and set of conductors. Okay, so now we have a questions. I will tell you what are the possibility question. So first one, what is the mean by the stationary magnetic field? Okay, so this is a one possibility question. And next one, what is mean by the relative time variation between the magnetic field and set of conductors? I think you heard one more word in the electrical machine, that is the relative motion between the magnetic field and set of conductors. So now we have a question, what are the difference between the relative motion between the magnetic field and conductor, or relative time variation between the magnetic field and conductors? So that part also we will going to be discussed here. And next one, the set of conductor. What is the meaning of set of the conductors? Are you getting my point? So what is mean by set of conductor? And the stationary magnetic field क्या है? And similarly the relation क्या है between magnetic field and conductors? Okay, so are you clear? Is that right? So now we will discuss in detail about the basic requirement that to induce the EMF in a transformer here. Suppose we have a conductors. So in this case, so we know that, so this is the set of conductor in the sense, listen, suppose we have a one conductor, okay, like, so this type of conductors, what we called here, so it is the state conductors, okay, and next one, so all the conductors are, okay, here wounded like this, so this is called the coil, okay, coil in the means, okay, it is the group of conductors, okay, or the set of conductors here, okay, this is the group of, and this type of conductor is known as the state conductor, okay, state conductor. And what about this type of conductor? So it is also conductor, but all group of the conductors, or this we know that set of the conductors. So group of conductor, it is known as coil, and the group of conductors here. So it is also called the circular conductors, okay, sometimes we can say that the circular conductors, the state conductors here. So we have the two theories are there. One is a Ampere's law, okay, this one is a Ampere's, okay, Ampere's law, and second one is the another part, the second one, so that is right hand the thumb rule, okay, this one is right hand the thumb rule here. So what is these two laws? What is the purpose of these two laws here? So basic laws, okay, in the magnetic circuit. So these two laws are, okay, Ampere's law gives, okay, magnitude of the flux, okay, this one, the only magnitude of the flux point. And what about right hand thumb rule? Okay, this will you can find out the direction of the flux in the magnetic field, okay, this one. So what is the Ampere's law? Ampere's law means a current carrying conductor produces magnetic field, okay, current carrying conductor. Ampere's law states that a current carrying conductor produces magnetic field around it, okay, and this magnet direction of the magnetic field can be obtained by using right hand thumb rule. So Ampere's law that states about the direction magnitude of the flux, but how do we find out the direction of this flux here? So that direction of the flux can be obtained by using the right hand thumb rule, okay. So this is the basic two laws, okay. So that what we conclude here, so that is a Ampere's law, okay, this Ampere's the law states that, okay, states so that a current carrying conductor, okay, very important, if you know this you can understand everything here. A current carrying conductor produces magnetic field, okay, this magnetic field around it, okay, and direction of magnetic field, direction of magnetic field can be obtained by using which law here? The right hand, okay, this right hand thumb rule, okay, it is also called another name of this one. So sometimes it is also called the screw rule or grip rule, okay, all are same, the right hand thumb rule, screw rule and grip rule here. All of you clear? So Ampere's law states that a current carrying conductor produces magnetic field around it, and direction of this magnetic field can be obtained by using right hand thumb rule. So now we have a question. So what are the conductors here? I already mentioned that we have two types of the conductors. One is the state conductor and second one is the circular conductor. So what is the difference between these two? That means how do we find out the direction of the magnetic field in the state conductor? And how do we find out direction of the magnetic field in the circular conductors? Okay, suppose in case of purpose of this rule, okay, this purpose of, so this rule is, okay, to find out the direction of the conductor. So next, direction of the flux. Suppose in case of, okay, state conductor, okay, this is the state, the conductor, then what will happen? So here is if the thumb indicates, okay, thumb, the indicates the current direction, orientation of the fingers, okay, this orientation of fingers indicates the flux direction. So if we know the current direction, then you can find out the flux direction in case of the state conductor. Similar way, in case of the circular conductor, that means coil. So in case of the circular conductor, so what will happen? How do we find out? So this is if the orientation of the fingers, the indicates current direction, so then this thumb indicates, okay, flux directions here. So this is the difference between the state conductor as well as the circular conductors. All of you clear my point? So in case of the state conductor, if thumb indicates current direction, suppose this thumb indicates current direction, orientation of the fingers around the conductor indicates flux direction. And in case of the circular conductor, suppose it is a coil, how do we find out the flux direction? If thumb if the orientation of the fingers around the conductor indicates current direction, then thumb indicates flux direction. Okay, so this is about the right hand thumb rule. So always we have a question, what is the purpose of the right hand thumb rule? The right hand thumb rule is used to find the flux direction in case of the state conductor as well as a circular conductors. All of it clear? So next, coming to the here, so let us take example point. Okay, so now we have a question, the example point. So we have one state conductors here. So this is this is our state conductors. So let us assume this end is A and this end is a B. Okay, this end is a B. So assume as the current flows in the state conductor from A to B terminals. Okay, like this. Current flows in the state conductor from the A to B terminals here. So now this length is length of, this one, the length of the state conductors, like so on. Okay, so what will happen according to the Ampere's law? Okay, Ampere's law state that a current carrying conductor produces magnetic field around it. So that, okay, here is so this is a magnetic field produces around these conductors, okay, like this. So now this is magnetic field, so around the conductors. So this direction of the magnetic field, how do we find out direction of the magnetic field? If thumb indicates current direction and this is a current direction, the upward direction, and what about the flux direction? Is it clockwise or anti-clockwise? Okay, tell me all of you, is it clockwise or anti-clockwise? Very simple. If we know the sequence is a very important to learn the subject. I am inserting one by one point, okay, in this topic. So that sequence is a very important to clearly know about the subject. Okay, so now tell me what will happen. What is the direction of? You should answer, you should respond. Then only I know that you got it or not. Anti-clockwise. Okay, the Nikita given anti-clockwise, Surendra and Krishna. Very good, very good. Anti-clockwise. Okay, anti-clockwise from above. Very good. So all of given anti-clockwise direction. So that, so according to the flux, okay, according to this, the right hand thumb rule, direction of the flux is a anti-clockwise direction. Okay, this is the flux around this conductor. Suppose here is a, so we have the another conductor, okay, same conductors like, so we have taken same conductor, but current flows from, okay, let us assume this terminal is a sorry, and this terminal is a B, right? So now length is a remain same, the current flows in this conductor, okay, it is a downward direction, okay, like this. So this is the current direction in a coil. So always according to the Ampere's law, so a current carrying conductor produces magnetic field around it. So now here is this is the magnetic field direction, okay. So one flux, all the flux lines are, okay, like this. So now how do we find out, okay, this direction of the flux? So which one? Is it a clockwise or anti-clockwise? The see here, thumb indicates current direction. Am I right? The always in case of the straight conductor, thumb indicates current direction. If thumb indicates current direction, then orientation of the fingers around the conductor indicates flux direction. So that flux lines are, okay, in the clockwise direction. So now this flux is a anti-clockwise direction and this one is the clockwise direction. So now which type of conductor here? Okay, this one is the straight conductors, okay, straight conductors here. So all of it clear. And next one, we have one more other type of the conductor that we can use in the transformer construction. The straight conductor is it is a only single conductor. So what about other type of the conductor? See, so suppose we have, okay, one magnetic core. So this is we have one magnetic core like this, okay. So let us assume it is a one magnetic core. Windings are placed, okay, some number of the turns. So now we are placing some number of the turns on the core, okay, like this manner. So we can place the whatever you want, and this is the some n number of the turns are placed. Okay, this is some n number of the turns. Okay, so now let us assume it is a positive current. Okay, this is a positive. So that means current enter at this position and leaves at this position. Suppose you can take, so this is the positive half cycle. Okay, like, so that is the positive half cycle here. So in positive half cycle, so definitely here this is the direction. Okay, positive half cycle of the magnetizing current. So the current required from the source to create the flux, that is known as magnetizing current. Already yesterday we have discussed this part. Suppose one case, okay, it is a magnetic core and this one is a coil. So current is a positive half cycle. So definitely what will happen? Current enters. So what is the current directions here? Okay, this is the current directions. Okay, so this cross in the means current entering position and dot here current leaving position. So where the what we conclude here, the where the cross mark indicates current entering position. Okay, entering the position in the coil, and similarly dot is a current leaving positions. Okay, so these two are current entering and leaving position. So under this condition what will happen? According to the Ampere's law. Okay, what is Ampere's law? The current carrying conductor produces magnetic field around it. So definitely, so here is a current carrying conductor produces magnetic field around. So how do we find out, okay, this direction of the magnetic field? So now definitely current carrying conductor produces magnetic field. Okay, magnetic field around it. So now this is a, suppose the we have the conductors. So this is all the flux lines. So just assume as, so how do we find out direction of the flux in the circular conductor? If the orientation of the fingers, okay, this is the right hand. So these are orientation of the fingers. and this one is a thumb. So if the orientation of the fingers indicates current direction, then thumb indicates flux direction. So that flux lines are passing. Okay, this is the flux lines are passing, okay, from my right to the left, okay, this position. So now these flux lines are, okay, passing and come back to the south. So now this is known as, okay, here. So it will become, okay, here is okay, this is act as a south pole and this one is act as a north pole here. So always the flux lines are passing within the magnet from south pole to the north pole. So this type of magnet is known as electromagnet, okay, electromagnet. It is not a permanent magnet. So we are excited with a supply and this core will become as a magnet, that is known as electromagnet here. Now similar way, suppose in the negative half cycle, what will happen? So now this is the flux lines or the region around the magnet is known as the magnetic field. So this, which type of this conductor here? So this conductor is known as the circular, the conductors. Got it? So now we have a question. Suppose if it is a negative supply, the negative half cycle of the magnetizing current, then what will happen? So let us take same, okay, we have the core, okay, suppose we have one magnetic core and windings are placed on the core. Okay, we have placing some the winding placement of the winding is remain same. So we are placing winding on the core as shown in the figure. Suppose it is a negative half cycle, so then what will happen? This will become minus and this will become plus. Okay, so this supply is the negative half cycle. Okay, negative half. So now this is the negative half cycle. So negative supply is provided. So now what about current entering position? This is the current entering and current comes from here. So here is a current entering. Okay, this current enter. Suppose we have so like this type of the core. So here current enter at bottom of the core. Okay, and comes up from the top of the core. So like that, so that this is the current directions. So now here all current entering position, this is the current entering position and this one is the current, the leaving position. Current entering and comes out. So how do we find out the direction of the magnetic field? So the region around the magnet, the indicates. So current entering and leaving. So that always flux lines are, okay, passing. So this is the direction of the flux. Okay. So now whatever flux here comes back, okay, like this. So now this type of, this pole will become south and this is the north. Okay, all the flux lines are the passing from south to the north within the magnet, outside the magnet, north to the south. Okay, like. So this is a per positive half cycle and negative half cycle. Okay, is that clear? Any more question? Do you want to ask? Very simple, don't confuse. In case of the state conductor, okay, always right hand thumb rule indicates, or purpose of the right hand thumb rule, it is used to find out the direction of the flux. In case of the state conductor as well as the circular conductors. So in case of the state, how do we find out direction of the flux? So here, if the thumb indicates current direction, then orientation of the fingers around the conductor indicates flux direction. But in case of the circular conductor, so if the orientation of the fingers indicates current direction, then thumb indicates flux directions. Okay. So this is about, okay, so in case of the, okay, state conductor as well as a circular conductors. Suppose according to the Ampere's law, okay, Ampere's law, so that according to, okay, Ampere's law, see here, Ampere's the law, how do we find out this magnetic field? So here is a, so that integral of HDL, ఒక HDL length integral of the HDL is equal to current passes through the conductor. So this is the current that passes through conductors. Okay, alaphi clear? Okay, similar way this is in case of the single conductors. Suppose we have some n number of the conductors are there. So then how do we get the integral of HDL? Okay, integral of HDL, so that is equal to number of turns multiplied by that current passes to the coil. Okay, that current, which current here? Magnetizing current. So now if it is simplify this, so now H is a constant. Okay, integral DL is equal to the number of turns multiplied by current. So now therefore H is equal to, okay, this is the number of turns by the length of the core. Okay, length of the core. So let us assume this is the equation 1. Okay, equation 1. So now we know, okay, here is so we know that, okay, we know, so according to the Biot-Savart's law, the B is equal to the nu H, okay, where nu is a permeability of the core. Okay, in this case, so where the nu is a permeability of the core, that is equal to nu naught and nu r. So relative permeability and permeability of the free space. So that value is equal to 45 into 10 to the power of minus 7. So now this is a, we can say here. So let us assume here equation 2. So now substitute the equation 2 in the equation 1. So we get, okay, B we can write, okay, flux density. So that B we can write. So flux by area and the permeability, and H you can write, okay, Ni by the length of the core. Okay. So now from here flux is equal to, okay, in this case the number of turns multiplied by magnetizing current and length of the core, permeability of the core multiplied by area of the core. Okay. So what about this value? Okay, here is so this one we can say that, okay, Ni. So it is a MMF, okay, MMF. So divided by, so this is called the reluctance of the core. Okay, it is nothing but the reluctance. Okay, it is analogous quantity of the resistance, the reluctance of the core. So that, so what we conclude here, if flux is okay, therefore, so if magnetizing current I nu is equal to Im sin omega t, okay, sin omega t. So then what will happen? The flux phi of t is equal to, okay, this I nu of t is equal to, so therefore phi of t is equal to the number of turns, okay, Im the sin omega t, okay, divided by the reluctance of the core. So now simplify this, okay, phi of t is equal to, so now here this one is a n, okay, so this you can write directly pi maximum, okay, sin the omega tn. So this type of the flux you can say that the relative time variation. So why it is relative time variation? See here. So why we can call the relative time variation? So we know that the frequency, for example, the for 50 Hz frequency, f is equal to 50 Hz frequency. Okay. So now what is the time period? 1 by the frequency here. So now this is the time period is equal to t is equal to 1 by f. So 1 by 50 is equal to 0.02 second. So now this is equal to 20 milliseconds. Am I right? Okay, 20 milliseconds. So now in this case, okay, at t is equal to 0. Okay, at t is equal to 0. So that means 20 millisecond at t is equal to 0. What is the flux here? Phi of t is equal to that 0. Similarly, at t is equal to the here is okay, 20 milliseconds means, so in this period, so 0, okay, that this one is the 5 milliseconds, the 10 milliseconds, okay, 15 milliseconds, and this one is the 20 milliseconds. So now it is the time t, okay, this one is the time magnetized flux here. So at 5 milliseconds, okay, flux will become pi of t is equal to the maximum value of the flux. The similarly at t is equal to 10 milliseconds. Okay. So then what will happen? The flux pi of t is equal to the again will become 0. So now at t is equal to, okay, this 15 milliseconds. So now what will happen? Pi of t again, get the maximum, the negative ones. So now at t is equal to 20 milliseconds, okay, this pi of t is equal to, so that will become 0. So here in every half cycle, flux changes from with respect to the time. So in every, okay, in the every cycle, okay, this one is a every cycle of the supply, the flux change, okay, this flux, the change with respect to the time. So this is known as the relative time variation between the magnetic field and the set of conductors. Okay, so that what is the conclusions here? Already have discussed very clear. See, okay, so now we have a question. The set of conductors, that is the group of the conductors. Am I right? Next, stationary magnetic field. That means magnetic speed of the magnetic field is equal to the 0. And relative time variation between the magnetic field and set of conductor. In every cycle of the supply, okay, in each time period. So now flux changes with respect to the time. The magnetic field is a stationary, conductor is also stationary, but flux produced in the magnetic field must be varied with the time. So this type of relation is known as the relative time variation between the magnetic field and set of conductors. Okay. So now have we clear my point? How do we find out direction of the flux? Direction of the flux can be obtained by using right hand thumb rule, and magnitude of the flux can be obtained by using the Ampere's law. Okay. So that what is the formula to get the flux here? Flux is so this is the formula to find out the flux. Always we can write flux is equal to mmf by reluctance. Okay, this is the, so flux we can write, so therefore the flux is equal to mmf, ratio of mmf to the reluctancy of the core. Any more question do you want to ask? This is only about direction of the flux, magnitude of the flux. The still we will discuss about magnitude of the induced EMF and direction of induced EMF. Okay, so now we will discuss how does EMF induced in the coil. First we will take how does EMF induced in the coil, then how do we find out direction of that induced EMF. How does EMF induced in a coil and how do we find out direction of the induced. I am not talking about transformer winding, that part we will discuss, okay, after this point. How does EMF induced in the coil and how do we find out direction of induced EMF or polarities of the induced EMF. Okay, suppose we have a one circular core, okay, and winding, some n number of the turns are placed on the core, okay, like this. So we have a one circular core, so n number of the turns are placed on the core. All of it clear? Suppose this is a, we can say that the circular core, okay, circular core, and some technically it is known as the toroid. It is also called the toroid. Sometimes we have a question, what is the length here? The mean length of the toroid. So mean length of the toroid. How do we get mean length? Suppose we have a, okay, this center and this radius is a inner radius. Okay, suppose we have a question. Okay, this one is a, okay, here. So this is the inner radius Ri and this one is a outer radius. Okay, outer radius here. So that is a Ro. Okay, like. So now how do we find out the mean length here? So this is the mean length means, so this is the length is equal to 2 phi r, periphery of the core. So that is the r mean. So how do we get this? The radius, mean radius here. So that is equal to the Ri plus Ro divided by 2. So inner radius and outer radius. So this part is a very important. Okay, this is the mean length and here. Suppose area we can find out. Okay, what is the area here? Okay, this is the area. So how do we get area here? So that is the area of the core. So that is equal to, so it is a phi r. Okay, mean square. Okay, this is the area. So that is the designing parameters of the circular core. So that is not our question. So our question is, how does EMF induces in the circular core and how do we find out polarity of the induced EMF? So whenever a coil is excited with the AC supply, then what will happen? Okay, whenever the coil is excited with the AC supply, what will happen? The see here, the when a coil is excited with the AC supply, so what will happen initially? The time varying nature of the current. Okay, this time varying nature of the current, so passes through the coil. Okay, that current you can say that magnetizing component of the current. So this current passes through the coil. Okay, what about the direction of this current? So all the current passes through the coil like so on. So this is the direction of the current. Okay, so it is the current entering position and this one is the current leaving position. Cross mark in the sense always the current entering position. Okay, this is the entering, where dot here sends current leaving positions. Okay, cross mark indicates current entering position. So here is a, how do we find out? A current carrying conductor produces magnetic field. Okay, magnetic field around it. Okay, this is the one. But how do we find this direction of this magnetic field? By using right hand thumb rule. So according to the right hand thumb rule, so this flux lines, okay, passes through. This is the flux in the coil. So which flux here? Time varying nature of the flux. Okay, pi of t and this is the I nu of the t. So flux the produces here. After that, what will happen? Whatever flux produced in the coil, okay, produced in the coil also links in the number of the turns. So how many number of the turns? N number of the turns. So let assume, okay, here the N is the number of the turns. Okay, number of turns of a coil and I nu of T is the magnetizing current. Okay, here magnetizing current, okay, or time varying nature of the current, and phi of t is equal to is the nothing but the flux, okay, the time varying nature of the flux. Okay, so now whatever flux produced in the coil also links with the number of the turns. So according to the Faraday's laws of electromagnetic induction, EMF induces in a coil. So that what is the step by step procedure here? The initially supply, when coil is excited with the AC supply, the MMF setup initially, right? Okay, MMF setup. So and after that, the here MMF in the sense the number of turns multiplied by the magnetizing current, and after that flux will be created. So what is the flux here? It is the ratio of MMF divided by reluctance of the core. So this is equal to number of turns, okay, magnetizing current, so divided by the reluctance of the core. So now simplify this, okay, phi of t is equal to, so this is the n, okay, you can write Im sin omega t, okay, divided by the reluctance of the core. So therefore phi of t is equal to phi maximum the sin omega t. So this phi maximum is equal to the when Im by the reluctance of the core. So in this case, the where the phi maximum is equal to N into I nu by magnitude of I nu by reluctancy of the core. So this is the flux, but according to Faraday's laws of electromagnetic induction, so now flux linkage is what? Okay, this is a flux linkage, and after that the flux linkage, okay, this flux linkage, the psi is equal to, okay, that is the number of turns multiplied by phi of t. So after this, okay, what will happen? Okay, after this one, so flux produced in the coil. So this flux linkage according to Faraday's laws, okay, according to Faraday's laws of electromagnetic induction. So EMF induces in a coil is a directly proportional to the rate of change of flux linkage. Okay, rate flux linkage is here. So now this EMF, okay, we can write. So now number of turns, the psi is what? Number of turns multiplied by phi of t. So now differentiation with respect to the time. So now this EMF, okay, if you remove this proportionality constant, this is a minus n, okay, d phi of t by the dt. So this EMF is known as, okay, this type of EMF is known as the statically induced EMF. Okay, statically induced EMF. So now question is, why this minus sign? Okay, it is a very important. So this y, okay, y minus sign here. Okay, this is a question. All of a clear point? Okay, one by one step, what will happen? So whenever a coil is excited with the AC supply, okay, whenever a coil is excited with the AC supply, the MMF set off initially and thereby flux will be created. So whatever flux created also links in the number of the turns. So that flux linkage form, and according to the Faraday's laws of electromagnetic induction, EMF induces in a coil. So that EMF is known as the statically induced EMF. So why it is statically induced EMF? So EMF induces in a coil, okay, due to relative time variation, okay, relative time, the variation between the magnetic field and the set of conductors. So that's why it is treated as the statically induced EMF. So there is a one more induced EMF, dynamical induced EMF. So that EMF due to relative motion between the magnetic field and conductor. That is in case of the generators, okay, not in the transformers, okay. All of it clear? So how does, okay, now question about, so this minus sign, okay, what minus sign indicates here? Okay, minus sign indicates, okay, this minus sign. So it indicates, okay, indicates Lenz's law. Okay, very important. Minus sign indicates the Lenz's law here. So what is the meaning of Lenz's law? So Lenz's law, it is a statement, is a, okay, statement. So now effect opposes, okay, effect opposes very cause producing it, very cause the producing it, okay, producing it here. So this is the statement, the effect opposes very cause producing it. So now we have to find out the polarity of the induced EMF. Okay, see here all of you, very important. Okay, so according to the Faraday's laws of electromagnetic induction, EMF induces in a coil, okay, this induced EMF, but we don't know what are the polarities. Magnitude we can say that. So magnitude of induced EMF, okay, this magnitude. So magnitude of, okay, magnitude of induced EMF okay, this is equal to, okay, here the n, the d phi by the dt, right? Okay, so this we can obtain by using Faraday's laws of electromagnetic induction. So this is the magnitude of the induced EMF. So then how do we find out the direction of the induced EMF or polarity of the induced EMF here? So how do we get direction of induced EMF here? Suppose effect opposes very cause producing it. So this is the current is a magnetizing current. Okay, this one is the magnetizing current. So induced current, okay, this induced current, the must opposes, okay, or clear point, the which one is the here, okay, direction of point. So here is a effect is, okay, suppose the effect is a the induced current, okay, this induced current, and what about the cause, okay, this cause is a the magnetizing current, okay, this one is the magnetizing. So magnetizing current, this is the direction of magnetizing current, clear point. So now what about induced current? So it must opposes the magnetizing current, okay, to satisfy the Lenz's law. So therefore in order to oppose, what about these polarities? Okay, this E will become plus and the minus. Okay, so I will give the one example also. Suppose another example here, effect is a the induced voltage, okay, induced EMF, and what about the cause? Okay, that is a applied voltage. Okay, these are effect and applied voltage. So that's why we can write E is equal to minus, okay, E1 values. Okay, suppose we have a one more question. So here is a, so this is the positive half cycle. See here all of you. So it is a magnetizing current, okay, and it is a T. So now we have a Z, maximum value of the current. So now initially 0, okay, it is a maximum, then come. So now in the whenever magnetizing current, okay, changes from the 0 to the maximum, okay, 0 to the maximum. So then what will happen? See here, when magnetizing current changes from the 0 to the maximum, so now here is a, this induced current, okay, induced current due to the induced EMF, so must opposes, okay, this is the opposes, okay, this magnetizing current, opposes the magnetizing current. That's why the polarities here positive and the negative. Suppose here is a, when magnetizing current, the changes from maximum to the 0, okay, from maximum to the 0. So now this is a, at this condition, the induced current, okay, in the direction of magnetizing current, direction of the magnetizing current only. So that we can write, okay, in general E is equal to plus or minus the n d phi by dt. Okay, this is the relation. So in general, suppose if I starts from here, okay, we have a 0 to maximum value, current progressively increasing. So which current is increasing? Magnetizing current. So in order to reduce this current, okay, in order to reduce this current, so what about this induced current must be in the opposite direction, reduced to the 0. Suppose whenever it decays to the 0, already it decays to the 0. That's why, so this induced current in the direction of magnetizing current. So it depends upon the position, the when from 0 to the maximum. So at this condition, the induced current opposes the magnetizing current. So when magnetizing current changes from maximum to the 0, the induced current in the direction of the maximum. So that polarities are, you can take minus or plus. But in generally, so we have calculated from initial point, from 0 to the maximum value. So that's why we have taken here positive and the negative. All of it clear? Very important. So why we have to find out the polarity? The effect opposes very cause producing it. Which one is the effect here? The effect is a current due to the induced EMF, and cause is a current from the supply voltage. Okay. So suppose we have a suppose we have the coil, okay, this is the, we have a coil. So now in this coil, okay, we are placing the bulb we are provided here, okay, one bulb is provided. So like this, example point I will tell you, see here, suppose if it is excited with the AC supply, okay, excited with the AC supply. So in the positive half cycle only, the current changes from 0 to the maximum. When it is a 0 to the maximum, okay, this bulb is the bulb will be glow, right? Okay, after some time what will happen? EMF induces. So in order to reduce, okay, this brightness of the bulb 0, so this current because of magnetizing current, so definitely induced EMF current, the must opposes, okay, this must be opposes when current changes from 0 to the maximum value, okay. So now this polarity is a positive and this polarity is a negative, okay. Now when current changes from maximum to the 0, what about this polarity here? Already it is reduced to the 0. So that's why it is in the direction of the in the direction of the magnetizing current. So that you can write directly the E is equal to plus or minus N d phi by dt. Okay, this is the, so actually plus you can write, minus also you can write, but in generally minus we have taken. What is the reason? So we have comes from the 0 to the maximum, not from the maximum to the 0. Is that clear? How do we take polarities of induced EMF? Whenever magnetizing current changes from 0 to the maximum, okay, in the positive half cycle, so definitely induced current opposes the existing magnetizing current. That's why we have taken, so to give this in this one we have taken positive polarity and negative polarity. Suppose if you consider from maximum to the minimum, okay, from maximum value to the 0, whenever current changes from maximum to the minimum value or 0 value, so here is it is in the direction of magnetizing current. That's why we can write the E is a plus or minus, but in general we have taken from starting point. Okay, is that clear everyone? So what we conclude here, the conclusions, the magnitude of induced EMF, conclusions very important, magnitude of induced EMF can be obtained by using Faraday's laws of, okay, electromagnetic induction, and that this is a polarity or direction of induced EMF, direction of induced EMF can be obtained by using the Lenz's law. So that means the effect opposes, the EMF induced opposes applied voltage to satisfy the Lenz's law. Okay, which one is the effect here? The effect is a, so EMF and cause is the applied voltage. That's why we can write, so if you apply the KVL equation also, we can get E is equal to minus E1. So this minus sign indicates Lenz's law. All of you clear? So now let us discuss about how does EMF induced in the transformer. Previously we have discussed about how does EMF induced in the coil and how do we find out direction of induced EMF. Now here also see here, let N1 is a number of turns in the primary winding, where N2 is a number of turns in the secondary winding of transformer. So whenever transformer is excited with a single phase AC supply, so what will happen? Magnetizing current passes through the winding. So this is the I nu current, magnetizing current. So this magnetizing current here, this is the current directions. Okay, it is a entering position and it is a leaving position. So according to the right hand thumb rule, okay, how do we find out the flux direction? Okay, just apply the flux direction here.
So just according to the right hand thumb rule, okay, this is the flux pi 1. So whatever flux produced here, which also links in the secondary winding through transformer core. Okay, this is the direction of the flux. So this is a phi 1 amount of the flux. So according to the Faraday's laws of electromagnetic induction, EMF induces in the primary winding as well as the secondary winding. So now this is the EMF, okay, E1 and here E2. So how do we find out this, the polarity of induced EMF? So this one is a, suppose we have considered as positive half cycle. So now the positive half cycle, that's why plus and minus. Okay, in the positive half cycle also, this magnetizing current changes from 0 to some maximum value. Okay, so we have considered this point. Okay, now at this condition, so now in order to oppose this magnetizing current, polarity is a positive and this polarity is a negative. So now this is the polarity of the induced EMF. So how do we get the polarity of this induced EMF here? Suppose if I connect the load, okay, here, so then what will happen? See, some current passes to the load. Okay, this current you can say that I2 current. So now it is a current entering, okay, like this. Okay, this is the current here. So this is the entering position. So this flux phi 1 here, okay, phi 1 is a effect, right? Okay, sorry, phi 1 is a cause to produce this value. So phi 1 is a cause, and what will happen due to this current? So one more flux is a produces, that is a N2 I2 divided by reluctancy of the core. So according to, what about find this direction of this flux here? So this phi 2 flux is a this direction of the phi 2. So now here phi 2 opposes, okay, phi 1. So this is a phi 1. If it is load is a connected. So that's why this polarity will become positive and this polarity is the negative one. So then how do we find out magnitude of induced EMF? So let us find this magnitude here. So V1 is equal to minus N1, okay, d phi 1 by, okay, dt values, okay, d phi 1 by dt. So now this one is a E1 is equal to the minus N, okay, d differentiation of the N1 phi 1 divided with respect to the time. So now it is equal to minus N1, so differentiation of the flux linkage with respect to the time. So therefore E1 is equal to it is a minus, okay, no need of here right, minus, okay, directly we can say that. So here is a, okay, E1 is equal to the minus dn. So therefore E1 equal to minus, okay, d psi by the dt. So now this equation minus, okay, d psi by di1 multiplied by di1 by dt. So now simplify this, okay, where E1 is equal to minus the which inductance? It is a self inductance, okay, self inductance, okay, di1 by dt. So now this EMF is known as the self induced EMF, okay, self induced EMF. Now similarly in the secondary winding, then what will happen? So here E2 is equal to minus N2, so d phi 1 by, okay, dt. So this equation you can rewrite, okay, minus the differentiation of the N2, the flux linkage with respect to the time. So therefore it is equal to minus, okay, differentiation of the, but is there any current here in the secondary winding? There is no current. So only primary flux, okay, that's why that here d the psi by, okay, di1 multiplied by, okay, di1 by the dt. So now which inductance here? So this is equal to minus m, so di1 by the dt here. So this is a known as the mutual, the induced EMF, okay. So that what we conclude here, EMF induces in the primary winding is a self-induced EMF. EMF induces in the secondary winding is a mutual induced EMF, okay. So that what we conclusions here. So the important for exams point of view. So first question here, so that is a EMF induced in the transformer, okay, nature of the induced EMF in the transformer. So that is a statically induced EMF. Okay. So it is a two types. One is a self-induced EMF. Okay, self-induced EMF, and second one is the mutual induced EMF. Okay. So now the EMF induced, okay, EMF, the induced in primary winding. So that which one here? Self-induced EMF. So EMF induced in the induced in secondary winding. So that is a mutual induced EMF. So these are all possibility of the question in competitive exams. Okay. All of you clear my point? How does EMF induced in the coil? How does EMF induced in the transformer winding? So whenever a coil is, when the primary winding of the transformer is excited with the AC supply, time varying nature of the current passes to the primary winding. So due to which flux will be created. So whatever flux produced in the primary winding also links in the secondary winding through transformer core. So according to the Faraday's laws of electromagnetic induction, EMF induces in the primary winding as well as the secondary winding. So how do we find out the polarities of, so these two, okay, polarities here. So polarities of these, the induced EMF. Suppose just imagine if the load is connected here, then what will happen? So this polarity, current passes through from here. So polarity of this, the primary induced EMF, polarity of the secondary induced EMF. So now magnitude of induced EMF can be obtained by using Faraday's laws of electron, and direction of induced EMF can be obtained by using Lenz's law. Okay. So now next one more question. The nature of induced EMF in a transformer, that is a statical induced EMF. So what is the meaning of statical induced EMF? EMF induces in a coil due to relative time variation, but not relative motion. The relative time variation between the magnetic field and set of conductors is known as statically induced EMF. And EMF induced in the primary winding is a self-induced EMF. So what is the meaning of self-induced EMF? EMF induces in a coil that due to current passes through its own, okay, that is known as self-induced EMF. And EMF induced in the secondary winding is a mutual induced EMF. So EMF induces in the secondary winding. So due to current passes through another coil, which the magnetically coupled through the same flux. Okay, that EMF is known as mutual induced EMF. Okay, so that what are the conclusions here? So nature of induced EMF in a transformer, that is a statical induced EMF. So EMF induced in the primary winding of the transformer is a self-induced EMF. EMF induced in the secondary winding of the transformer is a mutual induced EMF. Okay. Okay, is that clear, everyone? Yeah, no need to write. I will provide the PDF. Just listen always. That is a very important part. Okay. So let's discuss some questions based on this concept. Okay. So this is the one of the question here. So if transformer is excited with a square wave voltage source, then the shape of induced EMF will be, okay. Option A, sinusoidal wave, option B, square wave, option C, impulse wave, and option D, triangular wave. If transformer is excited with a square wave voltage source, then the shape of induced EMF, okay. Can you answer this? All of you try yourself. What is the answer for this question? Impulse wave. Okay. So impulse, if transformer is excited with a square wave voltage source, then the shape of induced EMF, okay, Premchand given C option, it is a impulse wave. Okay, let me check. The C here, when transformer is excited with a square wave voltage source, okay, the square wave voltage source means, okay, this is the square wave, right? Okay, it is a time t. Okay, positive the step, okay, this is a positive step, okay, negative step, positive step and negative step and so on. So this type of wave we can say that, okay, it is a square wave. Okay, if it is excited with a square wave voltage source, that means, so that is the Vs of, okay, Vs is the Vs of t is equal to the square wave. Okay, so given here, okay, given that, okay, given the Vs is the square wave, okay, square the wave, but we required the shape of the induced EMF. So we have to find out the shape of, okay, induced EMF here. Okay, so how do we find out the shape of induced EMF? So we know that the transformer is a pure inductive nature. Okay, so this transformer, so we know, okay, we know that the transformer is pure inductive nature. Okay, inductive nature, so that inductive nature, so voltage across the voltage, the across inductor, so that we can write, okay, voltage across the inductor, just means Vs is equal to the L, okay, D, the which current here, magnetizing current, okay, D, the S by dt here. So ds V of t, okay, this is the I nu of t. So now let us find, okay, this shape of magnetite. From here we can write I nu of t here, so that is equal to, okay, I nu of t equal to, so this is the 1 by, okay, sorry, 1 by L integration, okay, Vs of t, okay, dt here, okay, this is nothing but the shape of magnetizing current, okay, shape of the magnetizing current of the transformers. Now, but we required shape of the induced EMF. So how do we get shape of induced EMF here? So therefore, the shape of, okay, induced EMF, so this is equal to, okay, here. So how do we get? Already we know that, okay, that is the minus, okay, L, the self inductance, okay. So differentiation of the magnetizing current, so with respect to the time, okay, this is the formula, okay, self inductance, and this is the formulas. So now here given is a square wave, right? Okay, so now let us calculate, okay, let us find the shape of the magnetizing current, the shape of the magnetizing current, okay, I nu. So now this is equal to 1 by L, okay, integration, so that is the Vs of dt, okay, this is equal to 1 by L integration of the square wave, okay, with respect to the time, okay. So integration of the square wave, okay, what will happen? Integration of the square, anybody? The integration of the square will become the triangular integration of the step signal, okay, step signal is a ramp, so ramp, the continuous is the triangular wave, triangular, okay, wave. So next one, we required shape of induced EMF. So how do we get this shape of the induced EMF? So this induced EMF, okay, we can say that, so it is the minus L, so d I nu by the dt. So now substitute here, okay, it is equal to the minus L, the differentiation of the triangular wave, okay, with respect to the time, okay, so with respect to time. So therefore it is equal to E here, okay, this value is a E, so shape of induced EMF, okay. So now this part, okay, differentiation again, the integration then differentiation, so that you will get the only the square wave. So it is also called sometimes it is a pulsed wave. So options pulsed wave is given, that is also correct. Okay. So if transformer is excited with a square wave voltage source, so how do we find out shape of induced EMF here? So again initially integration, then differentiation, so that you will get the square wave. So some data is required to answer this type of the question. So always integration of impulse wave, okay, impulse the wave, so that will become the square wave, right? So next one, integration of, okay, second one, the here square wave, okay, we will get, so that is a triangular wave. Okay, next one, the third one, integration of triangular wave, so we get parabolic wave. So this is the data is required to answer this type of the questions. Good afternoon all. Ashwini Kumar, good afternoon. Okay, got it all of you? Okay, next one. Let's solve one more question based on this concept. Okay, if transformer is excited with a square wave current source, okay, if transformer is excited with square wave current source, then the shape of induced EMF will be, what is the answer? Option A mentioned that sinusoidal wave, option B square wave, option C impulse wave, and option D triangular wave. So now tell me what is the answer? Premchand, again the impulse wave. Transformer is excited with a square wave current source. So this is a directly mentioned that shape of, okay, here is, okay, shape of magnetizing current, okay, that is a I know. So the which is given in the question directly, shape of magnetizing current is a given. So therefore you can find out the shape of, okay, induced EMF, okay, this induced EMF E. So that is equal to minus L, okay, d I nu by the dt. So E, this is equal to the minus L differentiation of the square, okay, square wave with respect to the time. So now simplify this, okay, here the differentiation of the square with respect to the time is, so that is equal to impulse wave. So what is the meaning of impulse wave? So that is a positive impulse, okay, positive impulse, okay, negative impulse, positive impulse, like. So if it is excited with a square wave, the shape of induced EMF will become the positive, that is the impulse wave. Yes, you can get it. So last lecture 1 also there is a playlist, electrical machines by Bhanu sir. You can go through that playlist. You will get all this my class. Ashwini Kumar, you can get my previous class also. Okay. So is that clear everyone? So now let's discuss one more question. If transformer is excited with a triangular wave voltage source, okay, instead of the sinusoidal, if it is excited with a triangular wave voltage source, then the shape of EMF will be, option A square wave with 90-degree displacement, option B square wave with 180-degree displacement, and option C triangular wave with 90-degree displacement, and option D triangular wave with 180-degree displacement. Okay, now tell me the answer.
Try yourself. It may be wrong or right. Try yourself. Then I will tell you. Yes, option B, square wave. We have a two options, square wave with 90-degree displacement, square wave with 180-degree displacement, and option C, triangular wave with 90-degree displacement, triangular wave with 180-degree displacement. Option B. Okay. So here is a given that the triangular wave voltage source. Okay, this means the given in this question. Okay, given the shape of the supply voltage. Okay, shape of the Vs. So that is the triangular wave. Okay, this is the triangular. Okay, triangular wave. Got it? So now we required the shape of induced EMF. So how do we get shape of induced EMF here? So we know the formula. Here is so let us find first one, that is the shape of the magnetizing current. Magnetizing current. So that is a I nu values. So let us find out shape of magnetizing current. So it is equal to the, how do we get 1 by L integration Vs the dt. Okay, integration of the supply voltage with respect to the time. So now therefore 1 by L integration the square, here is the triangular wave. Okay, so with respect to the time. Okay, with respect to time. So this is the only shape of the magnetizing current. Okay, so, but we required shape of, okay, here shape of induced EMF. Okay, induced EMF. Am I correct? So shape of the induced EMF. So it is equal to minus L. So di nu by the dt. So it is equal to minus L. The differentiation of, okay, this one is we will get, it is a parabolic wave. Parabolic wave. Okay, by simplification. So now here the differentiation of the parabolic wave. So with respect to the time. So that it is a triangular wave. Okay. Now question is, we have two options, triangular wave with 90-degree displacement, triangular wave with 180-degree displacement. So now which one is a correct? Which one is a correct? Triangular wave with 90-degree displacement or triangular wave 180-degree displacement? So now here is initially already I have mentioned that flux is phi 1, magnetizing current is in phase with the flux. So now transformer is a pure inductive nature. So that's why magnetizing current lags the applied voltage by the 90 degrees. Okay. So now what about EMF here? EMF lags the flux by the 90 degree. So now this, the here phi 1 is equal to phi maximum sin omega t. So this E1 is the suppose E maximum the sin omega t minus pi by 2. I will tell you this part in the next classes, vector diagram. So but what about the phase displacement? Here the phase displacement between the applied voltage and induced EMF, that is equal to 180 degrees. So that's why what is the answer for this question? So here is a triangular wave with 180 degree displacement. Okay. Next one. So similar question. If transformer is excited with a triangular wave current source, transformer is excited with a triangular wave current source, then the shape of induced EMF. What is the answer? The square wave with 90 degree displacement, square wave with 180 degree displacement, and option C triangular wave with 90 degree displacement and triangular wave with 180 degree displacement. So first what was given in this question? Okay, here is
that current wave. Okay, this is the triangular wave current source. So here given directly, so given that, okay, it is a shape of magnetizing current. So this is the shape of magnetizing current. So now let us find out the shape of the shape of magnetizing current and shape of induced EMF. Okay, so this induced EMF shape, how do we find out? So that is equal to minus L, okay, d I nu by the dt. So differentiation of the triangular wave, okay, triangular wave with respect to the time, so that we will get the square wave. Okay, square wave. But what about the displacement? So between the, okay, this already I have mentioned that. So flux, the magnetizing current, and it is a EMF and supply voltage V. So displacement between these two, okay, that is equal to the 90 degrees. So now E1, the lags the I nu by the 90 degrees. Okay, so that answer is the square wave with 90 degree displacement. Okay, so now let us solve one more question. A single phase transformer has 100 and 200 turns in primary and secondary winding, okay, respectively. The variation of the flux with respect to the time is given by phi of t is equal to minus 0.05 t square minus 2t Webers. The EMF induced in the secondary winding will be. What is the EMF induced in the secondary winding? So number of turns given in the secondary winding. So here EMF induced in secondary winding, so that is equal to E2, okay, EMF induced in the secondary winding. So with that formula here, minus N2, so d phi by the dt, okay, differentiation of the flux with respect to the time. So this phi, okay, differentiation of the given here, the phi of t is equal to, okay, flux is given, the phi of t, so it is a minus 0.05, okay, t square minus 2t Webers, okay, this one is a 2t square minus 2t Webers. So now let us find out the simplify this, okay, minus, okay, 0.1 t. So now this is the 0, sorry, this one is a the minus 0.05 t square minus the plus 0.1 t. Okay, so now let us find out the differentiation of these two. So this differentiation of the flux with respect to the time. So with respect to time, so this is equal to the minus 0. Okay, this is the 0.1 t, the plus 0.1, okay, this value. So we required EMF, okay, E2 is equal to the minus 200, okay, into, so d phi by dt minus 0.1 t plus 0.1. So now this is equal to how much? The E2 is equal to the 20 t, okay, minus, okay, this one is a 20. So therefore it is equal to 20 into t minus 1 volts. So that answer for this question is the 20 into t minus 1 volts. Okay, so very good. Suppose we have a question like, one more possibility of the question, okay, a single phase 50 hertz transformer as number of tons of 100 and 200 in primary winding and secondary winding, respectively, okay, respectively. So variation of flux with respect to the time, with respect to the time is given below, figure. Okay, given below figure. Suppose figure given like this. Okay. Okay. So as shown in the below figure, okay, it is the flux pi of t is equal to 0.2 amperes. Okay. So now find out the magnitude of, okay, find out induced EMF in primary winding and the secondary winding in the intervals from the 0 to 1 second. 0 to 1 seconds like. Okay, now find it. How do we find out here from the intervals from the 0 to 1 second? So we know the formula here, the E1 is equal to minus N1 d phi 1 by dt, right? The similarly, the E2 also equal to minus N2 d phi 1 by d phi by dt. So we have to find out the slope of the line. Okay, this d phi by dt in the sense, so where the d phi by dt, okay, this d phi by dt here. So d phi by dt in the sense slope of the line. Okay, this is there. So which slope here? Positive slope. Okay, progressively increasing. So that's why you can say that the positive, the slope of line, okay, slope of the line, okay, from the here, which from the 0 to, okay, 1 intervals, okay, that positive slope of the line. So let us calculate positive slope of the line here. So therefore it is equal to, okay, this value is equal to y2 minus y1 by x2 minus the x1 value. So what is the y value here? 0.12 minus 0. So that is equal to 0.12 minus 0 divided by the x2, this is the x2 is a 1 minus 0. So it is equal to 0.12. Okay. So this is the only d phi by dt. So let us calculate the V1. The V1 is equal to minus 100 the into 0.12. Okay, 0.12. So therefore it is equal to minus the 12 volts. The similarly the V2 is equal to minus N2. So N2 is at 200 into d phi by dt. So that is equal to how much? 0.12. So that it is equal to minus 24 volts. Okay. So this is also another possibility of the question. Okay. Is that clear? Okay. So we have some more questions. We will discuss that part tomorrow. Okay. This is the concept we have discussed today. So one is what points we have discussed. How do we find out the direction of magnitude of the flux, direction of the flux. Similarly, how do we calculate magnitude of the induced EMF, direction of induced EMF. Okay, magnitude of the flux can be obtained by using Ampere's law. Direction of the flux can be obtained by using right hand thumb rule. So magnitude of induced EMF in a coil can be obtained by using Faraday's laws of electromagnetic induction. Direction of that induced EMF can be obtained by using the Lenz's law. What is the mean by Lenz's law? The effect opposes very cause producing it. Very means the initial cause. Okay, that's why the induced current, induced current in the primary winding opposes the current due to the supply voltage. That's why polarities we have taken positive to the negative. But we have consideration is a magnetizing current increases from 0 to the maximum value. Suppose at this point, suppose if you take magnetizing current maximum to the minimum, that is the maximum to the decays to the 0, that time polarities will be reversed. That's why we can take any one, plus or minus. But initially we have always considered from the starting point. So that means 0 to the maximum value. That's why in general we can take minus sign. Okay. And after that, that is a very important part. So the remaining part we will discuss tomorrow, and tomorrow we will discuss about, till now we have a discussion about how does EMF induce, okay, in the windings. Tomorrow we will discuss EMF equation of the transformer and what are the possible questions from the EMF equation of the transformer. That part we will discuss tomorrow. Okay, thank you all, thank you very much. I hope you like this session. Okay. Thank you very much. Okay, no problem. Those students who are new in my class, just go through previous class once and see this class. You will get it everything, and attend my classes regularly. You will get electrical machine very easy manner. Okay, I don't want to make you difficult in the electrical machine. I always thinks to reduce, that simplify. Okay, I will make it is very easy to this easy to you about this subject. Just continuously come to my class regularly, then you will get everything in the electrical machine. Even you don't know anything about electrical machine, you can also learn. You don't need any EMF theories and everything, but I will discuss everything. We don't know actually, some students think that I don't know magnetic circuit, how can I understand the transformer? No need, I will discuss everything whenever it is required. ओके और कुछ सवाल है आपके पास? आप कुछ भी सवाल पूछ सकते थे, हिंदी और इंग्लिश दोनों में. Ajit, okay, just come to class and you will get everything. You don't bother about the exam, everything will be fine. Okay guys, we will meet tomorrow at same time. Thank you all, thank you very much.